Hello everybody, and welcome to our last video on projections and datums. So far we've learned about projected and unprojected data. We've talked about reasons and strategies to take when projecting data, and the fact that all projected coordinate systems are projected from some underlying geographic coordinate system. We learned that there are almost 1,000 geographic coordinate systems recognized by ArcGIS, all of which position the spheroid in a different place relative to our little blue marble that we call home, and most, but not all of which, place the zero longitude point at Greenwich, England. We learned that ArcGIS easily handles data and maps in different projections, showing them to you all lined up correctly without ever letting you know how tough that was to do. But it does not handle data from different geographic coordinate systems as easily. The problem is usually that ArcGIS knows several different methods to transform data into different geographic coordinate systems. This process is called setting a geographic transformation, and ArcGIS needs you to pick the one to use. We saw that ArcGIS will attempt to sort the different options such that the best choices are at the top, but you can't always rely on that, and so there are sources available to look up what geographic transformations are best for different parts of the planet. In the last video, we saw how to set different projections and geographic transformations in ArcMap so that visually the data line up correctly, and this is useful for some types of analysis, like performing spatial selections and for making accurate maps. But now we'll look at how to actually project your data sets into new coordinate systems so that all your data line up correctly without any required transformations in ArcMap. This is a more reliable way to be sure that ArcGIS is performing the analysis in the way you expect and using the coordinate system you want it to use. Alright, moving on. We've been discussing how to set up ArcMap to show you the data correctly, to make it line up correctly in that data frame. That's all about viewing the data and making maps that look right. Next up, we want to consider how to analyze data, and that means we need to be able to change the coordinate system of the data itself. This idea of reprojecting your data, you do this when you're analyzing data, such as calculating areas of polygons or lengths of lines. You should project your data into a coordinate system that is appropriate for your analysis. So you might pick an equal area coordinate system if you're interested in the areas of wildlife habitat or stand boundaries. Now, when you reproject your data, you don't change your data at all. Your data stays safe. To reproject your data means you create a brand new data set that is in that new coordinate system. And ArcGIS has some nice, easy tools to do it. The question of geographic transformations does still come up. If you're going to project into a coordinate system that is based on a different underlying geographic coordinate system than it's starting from, then you're going to have to tell it the correct transformation. So here's where they are. If you open up the Arc toolbox, it's in the Data Management Tools toolbox, and then the sub-toolbox called Projections and Transformations. There's different tools for projecting raster data and vector data. The raster data is in the little raster subfolder, and the vector projection is down below that. Now, occasionally you actually have to define a coordinate system for a data set. You usually have to do this when the data comes from some really old source, back in the 80s, 70s, or 80s. Back then, GIS system was not able to transform data on the fly, so you could never load data sets in different coordinate systems into the same GIS session. Since the software wouldn't handle it, they didn't even write the coordinate system into the data set itself. It was just kind of up to you to know that all the data were in the correct coordinate system. Well, if you do a project and you wind up with data from those old days, well, you're going to have to tell ArcMap what coordinate system it is. And so here's a tool where you actually write the coordinate system information into the data itself. It's that define projection tool. Now, to project data is pretty simple. You just load up this little window here. You pick the input data set, you pick what you're going to name it and where you're going to put it, and then you declare the output coordinate system. If your output coordinate system is coming from a different geographic coordinate system, then you need to set a geographic transformation. So make sure you do this. Where it says optional, that's only optional in the sense that if you're projecting into something that has the same geographic coordinate system, then you don't have to do it, and there's no point. That's the only optional that's really going on here. If you're moving to a different geographic coordinate system, yes, do set a transformation. Now, raster data. Raster, the tool to project raster data looks a lot the same, but there's an option at the bottom for resampling technique, and this is important. First off, remember there's special things about raster data. Whenever you project a raster, you are going to change that raster. The raster will not be the same. You're probably going to get different numbers of rows and columns. You're probably going to get different cell values in each cell. This is because rasters cannot be projected as precisely as vectors can. They're not defined by precise points. Remember, rasters are a bunch of rows and columns. Vector objects are defined by highly precise vector vertices. Rasters are not that way. When you project a vector into a new coordinate system and then you project it back, you're probably going to get something that's pretty much exactly the same as the original. If you project a raster into a new coordinate system and then project it back, it will never be the same. It will have changed. Now, this means if you want to do an analysis that combines vector and raster data, you have a bunch of sample points. You want to know what the vegetation type is at each sample point. The veg type is a raster and the sample points are vector. Well, if those come from different coordinate systems, it is almost always better to project the vector data into the raster coordinate system rather than the other way around. Remember, when you project rasters, it's going to change. You want to leave that unmolested if you can. All right, so let's understand this issue a little bit. So here's your raster. Here's a bunch of rows and columns. When you project it, the new raster will still be a bunch of rows and columns, but they will be moved. They'll be rotated a little bit. The sizes will be shifted around. The question becomes, how do you transfer the data from the original raster to this new raster that is a whole new sets of rows and columns? Each new cell from the new raster covers parts of several old cells. So, yeah, how do you transfer the value? I'm going to try and illustrate some issues with this by, instead of looking at the raster boundaries, I'm going to look at points representing the cell centers. So, that raster projection tool offered you several methods. You could use a nearest neighbor, bilinear interpolation, cubic convolution, or majority. So these are the four methods that you can use to transfer the original cell values to the new raster. So what do these mean? Well, nearest neighbor is the simplest one. Your new cell is blue, your original cell is green, so the new blue value is just taken from the closest original green value. Pretty straightforward. The bilinear interpolation is completely different from that. It takes a 2 by 2 cell neighborhood and does an averaging function called bilinear interpolation. We're going to discuss bilinear interpolation in a few weeks. But basically this means that the new value is an average of those four original values. All right, so we've discussed two methods: nearest neighbor, bilinear interpolation. Nearest neighbor takes the exact value of the nearest cell. Bilinear interpolation takes an average of the four nearest cells. So, some real important differences between these two strategies. First, nearest neighbor, your new raster is going to have cell values that existed in the original raster. Every cell value in your new raster will have existed previously. Bilinear interpolation probably won't have. If each new cell is an average of a bunch of neighbors, well, there's good chance that the new value will never have exactly existed in the original one. So what scenarios would these two strategies work best at? Let's go back to nearest neighbor. Nearest neighbor is good for categorical rasters, where a raster is maybe a veg type, or whether this is urban versus natural versus farming versus water. Where the raster cell values are actually codes for some other concept. In this case, you would want the code value to be transferred to the new raster. If we did bilinear interpolation, well, if code value for ponderosa pine was 2 and the code value for mixed conifer was 3, and this was in the middle of a bunch of mixed conifer and ponderosa pines, well, then it would come up with an average value between 2 and 3, and that isn't one of the code values. So all of a sudden you get a value that has no code corresponding to it. So bilinear interpolation would just ruin a categorical raster. You would never want to use that. You'd just kill it. On the other hand, it's very good for something like continuous rasters like elevation or slope. In this case, if those are 4 different elevation cells, well, maybe it's a really good idea to take the average of those 4 to estimate the elevation at this new cell. So it really comes down to categorical versus continuous rasters. Nearest neighbor is good for categorical rasters. Bilinear is good for continuous rasters. Okay, now there's 2 more methods, and they're similar conceptually to what we just discussed. Cubic convolution is similar to bilinear interpolation in that it takes an average of the nearest cells, but instead of the nearest 4 cells, it takes the nearest 16 cells. Majority method is similar conceptually to the nearest neighbor in that the new cell will have existed in the original cell. Rather than taking the nearest cell, though, it's going to look at a 4x4 neighborhood and find the value that occurred most often in that neighborhood and assign it to this new cell. All right, so we got 2 general strategies. One will produce a new raster in which every cell value existed in the original raster. This is good for categorical rasters. The other will produce a new raster where every cell is some sort of averaging method of a neighborhood of original cells. And this is good for continuous rasters. Can you think of a reason why you would prefer, say, nearest neighbor over majority or vice versa? Or would you prefer bilinear versus cubic convolution? Remember, the difference generally between these 2 is that the size of the neighborhood. Well, think about that. Consider it. We can discuss it. But I do want to mention one other thing. The methods that produce a new raster in which the cell values all existed, majority and nearest neighbor, those methods are often not good for continuous rasters like elevation or slope. And this is the problem you get. So here I'm illustrating this with nearest neighbor. The blue cells are the new cells, the green ones are the original. We start seeing cases where multiple new cells get the same value from the original. And these things usually happen on a repeating basis. The problem with this is that it just kills things like hydrologic functions. So if this is your elevation, then the fact that you have multiple cells all reading from the same original cell makes the new raster have a flat area. These are all the same elevations all of a sudden. And those flat areas can create these weird artifacts on the landscape that happen in repeating patterns. So curvature and slope, in both cases you can see this really weird grid pattern where the shape of the landscape is being affected by this repeating value issue. So this is just one reason why you don't want to project rasters if you don't have to. But even if you do have to project a raster, then if you have a continuous surface like elevation or slope, make sure you use bilinear interpolation or cubic convolution as the method. Okay, and that's it for projections and datums. Thanks so much for your attention. We'll talk to you soon.